In this video, we're going to be talking about atomic force microscopy, or AFM for short. AFM is a specific example of a more general family of techniques known as scanning probe microscopy, all of which involve a physical probe that is scanned across a specimen to characterize it. Other examples of scanning probe microscopies include scanning tunneling microscopy, or STM, and some less common ones such as SECM, SSM, and MRFM. An AFM consists of a micro cantilever arm that is connected to a tip on the end, typically composed of a material such as silicon, and that has a width on the order of nanometers. The cantilever arm is connected to a piezoelectric mount that is used to scan the tip across the surface of the sample and also to control its Z position. The Z position of the tip is monitored with a setup that consists of a photodetector and a laser that is reflected off the back of the tip and received by the photodetector. Where the laser beam is received on the photodetector depends on the Z location of the tip. An AFM is typically able to achieve a resolution on the order of 1 angstrom. Typically, an AFM is operated in one of three modes that is determined by how the tip interacts with the surface. The first is contact, the second is non-contact, and the third is tapping. Now we will discuss the situation when the AFM is operated in contact or static mode. In this mode, the tip is brought into physical contact with the surface of the specimen, where it is then maintained as the tip is raster scanned across the surface. Again, the Z location of the tip is determined by the laser and photodetector setup. In this case, the tip is in the equilibrium position, so it lands in the middle of the detector and the piezoelectric mount does not alter the Z position. Then, as it is scanned, it will first encounter this raised location that will deflect the cantilever arm up, which results in the laser beam being reflected at a lower point in the photodetector, which indicates to the system that the tip has indeed gone up. Then, as it is continued, it will encounter this valley where the tip will deflect in the opposite direction. And so this time, the laser beam will be reflected and land in a higher location on the photodetector, thus indicating that the tip has gone down. The second operating mode, known as non-contact mode, is considerably different than the first in principle. In this situation, the cantilever arm and the tip are placed in a position such that they do not make contact with the surface. Instead, they're oscillated by the piezoelectric mount some distance away from the surface so that no contact is made. This has benefits in that there is no risk for damaging the sample and or the tip. Now, in order to obtain the topographical information of the surface, the frequency and amplitude of the oscillations of the tip are monitored. When the tip is over a flat location that is at the equilibrium position, it oscillates at its resonance frequency, whereas when it encounters a peak or a valley, it oscillates at a different frequency with a different amplitude that indicates the location. The third operating mode, known as tapping mode, is essentially a combination of the first two modes, contact and non-contact. In this setup, the cantilever arm and the tip are placed in a position such that when they do oscillate, at the bottom of the oscillation, the tip does make contact with the surface. Just like in non-contact mode, the topography of the surface is mapped by looking at the frequency and amplitude of the oscillations of the tip. When the tip is over a Z location that is at its equilibrium position, it oscillates at its resonance frequency, and when it encounters a peak or valley, it oscillates off resonance. One aspect of the AFM that makes it particularly versatile is the range of specimens it can image. Because it doesn't require a vacuum environment like an STM does, it can be applied to a lot more situations. Some examples include whole cells, individual biomolecules such as proteins and DNA, polymers, glass, and silicon, just to list a few.